Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young.
Chapter 10, Projective Transformations of Two-Dimensional Forms. Section 100, Various Definitions of Conics. The definition of a point conic as the locus of the intersections of homologous lines of two projective flat pencils in the same plane was first given by Steiner in 1832 and used about the same time by Chasles. The considerations of the preceding section at once suggest two other methods of definition, one synthetic, the other analytic. The former begins by the synthetic definition of a polarity, chiefly page 263, and then defines a point conic as the set of all self-conjugate points of a polarity, and a line conic as the set of all self-conjugate lines of a polarity. This definition was first given by von Staudt in 1847. From it, he derived the fundamental properties of conics and showed easily that his definition is equivalent to Steiner's. The analytic method is to define a point conic as the set of all points satisfying any equation of the second degree, homogeneous in three variables, x1, x2, x3. This definition, at least in its non-homogeneous form, dates back to Descartes and Fermat, 1637, and the introduction of the notions of analytic geometry. The oldest definition of conics is due to the ancient Greek geometers who defined a conic as the plane section of a circular cone. This definition involves metric ideas and hence does not concern us at this point. We will return to it later. It is of interest to note in passing, however, that from this definition, Apollonius, about 200 BC, derived a theorem equivalent to the one that the equation of a conic in point coordinates is of the second degree. The reader will find it a valuable exercise to derive for himself the fundamental properties of polarities synthetically, and thence to develop the theory of conics from von Staudt's definition, at least so far as to show that his definition is equivalent to Steiner's. It may be noted that von Staudt's definition has the advantage over Steiner's of including, without reference to proposition K2, conics consisting entirely of improper points, since there exist polarities which have no proper self-conjugate points. The reader may in this connection refer to the original work of von Staudt, Die Geometrie der Lage, Nuremberg, 1847, or to the textbook of Enriquez, Vorschläge über Projective Geometry, Leipzig, 1903. Exercises. 1. Derive the condition of Theorem 10 directly by imposing the condition that the quadratic which determines the intersection of the given line with the conic shall have equal roots. What is the dual of this theorem? 2. Verify analytically the fundamental properties of poles and polars with respect to a conic. Theorems 13 through 18, Chapter 5. 3. State the dual of Theorem 11. 4. Show how to construct the correlation between a plane of points and a plane of lines, having given the homologous pairs A, A', B, B', C, C', D, D'. 5. Show that a correlation between two planes is uniquely determined if two pencils of points in one plane are made projective respectively with two pencils of lines in the other, provided that in this projectivity the point of intersection of the axes of the two pencils of points correspond to the line joining the two centers of the pencils of lines. 6. Show that in our system of homogeneous point and line coordinates, the pairs of points and lines with the same coordinates are poles and polars with respect to the conic x1 squared plus x2 squared plus x3 squared equals 0. 7. On a general line of a plane in which a polarity has been defined, the pairs of conjugate points form an involution, the double points of which are the proper or improper points of intersection of the line with the fundamental conic of the polarity. 8. A polarity in a plane is completely defined if a self-polar triangle is given together with one pole and polar pair of which the point is not on a side nor the line on a vertex of the triangle. 9. Prove Theorem 3 analytically. 10. Given a simple plane pentagon, there exists a polarity in which to each vertex corresponds the opposite side. 11. The 3 points A', B', C' on the sides BC, CA, AB of a triangle that are conjugate in a polarity to the vertices A, B, C, respectively, are collinear. Chiefly Exercise 13, page 125. 12. Show that a polarity is completely determined when the two involutions of conjugate points on two conjugate lines are given. 13. Construct the polarity determined by a self-polar triangle ABC and an involution of conjugate points on a line. 14. Construct the polarity determined by two pole and polar pairs AA and BB and one pair of conjugate points C'. 15. If a triangle STU is self-polar with regard to a conic C squared, and A is any point of C squared, there are 3 triangles having A as a vertex which are inscribed to C squared and circumscribed to STU. Sturm, Die Lehre von den geometrischen Verwandtschaften, Volume 1, page 147.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.